Hello everyone, welcome back to the 5-Minute Tech channel. In this video, we will be talking about Zero Trust architecture. We will be building Zero Trust .NET microservice ecosystem using Keycloak, OPA, YARP, mTLS, and Kubernetes along with the Docker Compose orchestration. It is the target audience for this implementation would be developers, solution architects, your security engineers, and the teams moving from perimeter-based security to cloud-native microservices. Now, Zero Trust architecture is not a single product or implementation or an API gateway configuration. It is an architecture where every request to every resource must prove identity, satisfy least privilege authorization, use protected communication, and produces auditable evidence. So let's dive deep into it now. So the problem statement which we have is most applications begin with a perimeter security mindset. We put a firewall around the network and expose a gateway at the edge, and then tend to assume service inside the networks are trusted. The assumption does not work well for distributed systems or microservices. Now, in modern platforms, an order API or a service like an order API calls inventory, inventory calls another service, background workers, consumes Kafka events, API accesses database, and workloads which are continuously deployed in containers. If one internal workload is compromised, the flat trusted network can let that compromise move laterally. And the Zero Trust changes the question from is this request coming from inside our network to who's making this request, what resources are they accessing, and why should they be allowed, and can we verify it right now. That is the whole problem we're trying to solve with this implementation. So what are we building? In this video, we will be doing a simple order fulfillment platform. We will be using .NET for this implementation, .NET microservices. A user creates an order through a web client. The request reaches a YARP gateway, and the order API validates the token again, checks the internet access, asks OPA for a fine-grained decision, persists the order, and then calls the inventory and payment using separate service identities. Now, the core principle which we are trying to implement here is simple, which is a valid user token should be automatically make every internal API call trusted. Each downstream APIs independently validate who's calling, whether the token was issued for that specific API, what scope is granted, and whether the request is permitted for the target tenant and resources. So the implementation will span across 10 parts. The first part we'll be talking about is understanding the Zero Trust architecture. Then we will have an architecture overview. Part 3 will be your identity and tokens. We'll try to understand user identity flow. Part 4 will talk about the gateway and the API enforcement. Part 5 will talk about the fine-grained authorization with OPA. And part 6 will be service-to-service Zero Trust communication. Part 7, workload identity and mTLS will focus on. Part 8 will be your data or database and the events associated with it. Part 9 will be observability and auditing. And part 10 will be the implementation roadmap discussion. So part 1, trying to understand the Zero Trust or Zero Trust architecture does not mean that every system becomes unusable or that no services can communicate with another service. It means access must be explicit. For example, your order API, which we have been talking about, should be allowed to reserve inventory, but that is not because it is the same cluster or same VPC or the same subnet. It is allowed because it has a verifiable, workable workload identity, and it presents the correct token for the inventory API. It has the correct scope, and a policy explicitly permits the actions, and the result is a system that limits the problem radius. If payment API is compromised, it should not automatically be able to reserve inventory, update orders, and and read every database or publish to arbitrary Kafka topics or something like that. Now, the trust boundaries, if you say the user should be behind the gateway, gateway should be in front of our order APIs, which has access to OPA, inventory API, and payment API. And then there is an administrator for the platform, and the APIs have their own databases, that is the inventory DB, order DB, and payment DB, which have the streaming platform, that is Kafka and event consumers. Now let's talk about the architecture. I'll show you the architecture in detail now. So our architecture has different components. One is your edge enforcement point. Then we have Kubernetes / Docker Zero Trust Network plane, which is something which we will be setting up. Then we have our private application runtime, which hosts the different application areas, that is the order API, inventory API, and the payment API. We also have the identity and access plane in terms of Keycloak setup. We have event integration phase, wherein we have the Kafka setup in place, and then we have the audit and observability plane, where we collect all the telemetry data. So when the user signs in through a web client, which could be React or Swagger UI, he or she gets a bearer token coming in from your Keycloak. The Keycloak provides the bearer token, and that is OIDC authorization code plus PXE token. Whereas after that, that using the token, the user can do orders post. The post is something which goes through your TLS ingress, rate limiting, request limiting kind of setup, which and then following that there will be a TLS protected request through the gateway API, that is our YARP based gateway. The authenticated route then order creates the order. It goes to the payment API and subsequently enters the data in the payment service. And it also does is it validates whether the person has the access to uh, against the Rego policies, whether it belongs to specific tenant scopes, actions, resources, and provides the transaction context. On that basis, the order API generates the transactions, and the payment processing and the inventory update happens. And then subsequently, there are subsequent steps of updating the streams after an order is in place. And then there is a telemetry in place wherein we collect all the events that are happening. So as you notice that no component is called the zero trust product. Zero trust emerges from how these components work together. Keycloak answers your identity questions. OPA answers your policy questions. The YARP, that is the API gateway, and the APIs enforce access. And then we have network policy constraints, network reachability. Databases and Kafka enforce their own access rules, and OpenTelemetry gives us evidences and visibility. Now, this separation is important because it prevents one overloaded component from becoming a bottleneck, a single point of failure, or even a all-powerful security bypass. Now, OPA is designed to decouple your policy decisions from application code, while its HTTP API support fine-grained authorization integration. Now, Spire is designed to establish workload identity and support mTLS deployment between the workloads and so forth. Now, part 3, which is our identity and tokens with user identity flow. In this, let's begin with a user creating an order, and the web client redirects the user to your Keycloak using OpenID Connect authorization code flow with PXE. After authentication, Keycloak issues your short-lived access token, and then that token should contain only claims required by the APIs. Typically, the claim includes subject identifier and the tenant identifier, scopes, roles if needed, and the token issuer, intended audience, and the issued at time and expiry. Now this browser sends that access token to the gateway. The gateway then validates the signature, issuer, and expiry, audience, and required scope, and then it routes the request to order API. Now the order API does not blindly trust the gateway. It validates the JWT again, because order API owns the order resources. So this protects the resource even if the request reaches the service through an unexpected internal path. Now your OAuth 2.0 and OpenID Connect are supported options for token authentication in our implementation using ASP.NET Core application microservices, and we will be talking about in more details around that. Now next is your token claims. The issuer is ISS is the issuer. Our API should accept tokens only from the trusted Keycloak realm, and that is what is on the left hand side. Sub, it identifies the authenticated subject, that is our user called Alice. AUD or odd is the audience, and this is extremely important because a token issued for order API should automatically work at inventory API or payment API. Now scope indicates the operations requested and granted. For example, order.create. Tenant ID is something which will help in multi-tenant solutions, and it lets us ensure that the user from specific tenant cannot do the CRUD operations on some other tenant. And finally, your expiration have the limited lifetime, and we should use the short-lived access token to avoid placing long-lived secret inside containers or your browser code. Now, user token versus service token, what are the differences? The distinction is one of the most important part in our architecture, and the user accesses token represents a person, that is our Alice as a user. It might say Alice can create an order for ACME, that is the tenant which he belongs to, and a service token represents a workload. It might say the order API can call an inventory API to reserve the stock. Order API should not simply take Alice's browser token and forward it unchanged to every downstream API. That creates your excessive token reach and makes it hard to know whether the call was made by the user directly or by the trusted service on behalf of the user. Now instead, the order API obtains a narrow token intended specifically for inventory API. That token has a limited audience and scope. The inventory validates that it is receiving a token specifically for inventory API, and the caller is in fact the order API. Now part 4, gateway and API enforcement. This is something we have done with we'll be doing with the YARP gateway and its responsibility. Now YARP gateway is our edge policy enforcement point, or PEP as we call it. It provides the first enforcement layer, and it receives external traffic, validates access token, applies route level authorization rate limit request, and like adds a correlation identifier. Now, for example, the route post orders requires the scope orders.create, right? If the user is not authenticated, and it returns 401. If they are authenticated but lack the required scope, it is returned as 403. Now, however, gateway enforcement is not good enough, right? A gateway may be misconfigured, bypassed through an internal path or compromise. Therefore, each of these APIs, that is the example, the order API must have a capability of defending its own resources. YARP supports authentication and authorization before proxying the request, and route configuration can associate a specific authorization policy with the route. Now, resource API responsibility that we have been talking about. What is the responsibility of an API like an order API? The order API is the owner of its own order resources. Therefore, it makes the final application level enforcement decision. It validates the JWT token, then it checks the request context. Does the token contain orders.create, right? Is the audience actually an order API? Does the user's tenant ID match the tenant in the request is made? And is the order amount within the permissible limit? Is the user allowed to create this kind of order? These are some of the questions. which needs to be answered by the caller. Some of these checks are local and simple, while others belong to OPA, policy engine, because they represent business policy that should be centralized, version tested, and probably reused. Now, the example .NET setup which we will have will be something which which will be similar to this. If you're familiar with .NET services and the code we write in the pipeline or the middleware is something where we add authentication, add WTP error, and then add authorization with the policy which we can configure there. This is the first level of API protection in our ASP.NET Core. Similarly, there are other ways and you can do in other languages. The resource server trusts one issuer, our Keycloak realm, and accepts token only for the order API audience. The authorization policy requires your authenticated user, the order create scope, and a tenant claim. Now, this is not a complete authorization model. It is the fast local guardrail that rejects obviously the pre-invalid request before they reach the business logic or the external policy decision point. Now, part 5, you have fine-grained authorization with OPA. Roles are useful, but they are often not enough. A role such as order creator gives us a coarse-grained starting point, but enterprise authorization usually depends on attributes and context. Which tenant does the user belong to? Is the target resource in the same tenant? What is the amount? What operation is requested? Is user acting directly or service acting on behalf of the user? Is a step-up authentication requirement needed for a high-value transaction? Now, these are all the attribute-based access control or ABAC. OPA is strong fit because it lets us write these rules outside the application code and evaluate them consistently. OPA supports API authorization decisions that use fine-grained context-aware policy inputs. Now, OPA is a policy decision point, or PDP as we call it. It evaluates the policy, but it does not sit in front of the APIs and magically secures everything by itself. The enforcement points, the gateway and the resource API must collect context, call OPA, receive the decision and enforce it. Distinction keeps responsibilities clear. OPA owns policy evaluation, API owns request validation and resource loading, enforcement, error behavior, and auditing. Now OPA input model, every authorization OPA input model, every authorization request should have a consistent contract, like as we are seeing in the left hand side JSON. The subject is your authenticated user or workload. The caller is your immediate service making the request. The action is the business oriented, such as order.create, not merely an HTTP verb, and the resource includes your attributes needed to evaluate the decision, such as tenant, amount, status, ownership, etc. The input should be intentionally minimal. Now, example of Rego policy, as we have been talking that OPA works with the Rego. So this is the sample Rego policy for our demo. By default, access is denied, as you see in the second line, and the request is allowed only when the action is order create, the caller has the right scope, and the user tenant matches the resource tenant. Now, this is a simple example, but same pattern can support rules based upon ownership, relationships, segregation of duties, product eligibility, risk score, etc. Now, part 6 is our service to service zero trust. External API security is only half the story. In microservices, the most dangerous trust assumption is often east to west communication, that is service to service call inside the platform. Now, if order API can call every internal service just because it is inside the container, then compromising order API gives an attacker a broad path for lateral movement. Instead, the inventory API must know exactly who is calling, and it should accept the call only from the order API workload. It should require a token intended for inventory API itself with the scope inventory.reverse. It should verify tenant consistently and enforce any additional business policies. Client credential flow. So order API, as we are talking about, it will go to the Keycloak like, hey, I am order API. It will be issued a service token with the audience inventory hyphen API with the scope inventory.reserve. And then with that, it will call using the mTLS and bearer service token, the inventory API, which will probably identify it and return the response. Now, part 7 is workload identity and mTLS. Why we say that JWT alone is not enough. JWT validates a logical authorization grant, but it does not automatically prove the cryptographic identity of the workload at the other end of the network connection. Mutual TLS, or mTLS as we call it, means both caller and the receiver present a certificate. Each side verifies the other, communication is encrypted, and the peer can be identified. Now in our Kubernetes/Docker phase, Spire issues short-lived workload certificates. Service mesh or envoy sidecar uses these certificates to establish the mTLS automatically between the workload. Now network policies and mTLS, let's dive deep into it. There's a defense in depth. A multi-layered security posture is required wherein these controls overlap intentionally. Network policy controls which network paths are allowed. They reduce the accidental exposure and block many unwanted connections. mTLS proves workload identity and encrypts traffic. JWTs carry your user and service authorization grants. OPA evaluates the final business decisions, and none of these replaces the other. Network policy without application authorization is insufficient. JWT without the workload identity is insufficient. mTLS without your business authorization is insufficient, and zero trust is achieved through layered mutually reinforcing controls. Now, part 8 is your data and events. The zero trust must extend to databases, and each service should have its own database credentials and its own data boundary. Order API should not connect to payment API's tables directly. Inventory API should not use the super user credentials, and shared user application database account creates a larger impact radius and affects our auditability. Use separate database users, separate schemas and databases, least privilege grants, encrypted connections and secret rotations, and migrations owned by each services. Now, event-driven zero trust. Event-driven systems create another trust layer. A Kafka topic is not a trust internal pipe. Every producer and consumer requires an identity and narrow ACL. Service should publish only approved topic and consume only from the approved topics and consumer groups. Events must also be validated. Consumers should validate schemas, tenant IDs, producer identity, etc., and treat an event as untrusted input even when it arrives from an internal broker. So part 9 is our observability and audit, which is very important for every decision capture. If a system denies a request, operator must understand why. If it is allowed sensitive operation, auditors must be able to reconstruct who performed it, through which workload, under which policy version, and every gateway service, OPA decision, mTLS failure, and Kafka consumer should contribute correlated telemetry. We do not log raw access tokens, do not put sensitive customer data in logs. A record identifies and decision metadata that lets security team trace the access path safely. Now, what to monitor? These are not just operational metrics. They are security signals which you can observe. A sudden increase in wrong audience token may indicate a faulty deployment or attempted lateral movement. Repeated tenant mismatch attempts may indicate a broken client or an attack. Your OPA latency can become availability risk if the authorization is on the critical path, and your mTLS handshake failure can reveal an unregistered workload or a policy mismatch. So these will help you understand what is happening in your system. Now part 10 is our implementation roadmap on how we will be doing this implementation. For phase 1 is a local Docker baseline wherein we set up all these containers. Phase 2 is securing the vertical slice. So I'll be talking about how the Keycloak comes into picture along with OPA policy, and we evaluate certain calls. And the phase 3 will be the Kubernetes workload trust, wherein we can orchestrate using Kubernetes these layers to make the application concrete. Now, before we get into the demo, let's have a final message, and which is zero trust is equal to explicit minimal verifiable access. Now, this is very critical because every request must answer who you are, what resources are you accessing, which workload are you, and which actions you are requesting, why are you allowed, and can we audit the decision. So this will give you a full feature of a zero trust implementation. Now let's get into the demo and see how it looks like in actual work. Now this is our application code. We have set up the application layers. I've set up all the application layers, starting with your Keycloak realm JSON. It will have a client, different clients. First of all, it will create a new realm. It will have different roles as we were talking about. It will set up different clients. I'll be showing you the UI for this on the Keycloak. And then we have Rego files for each of the services, the inventory Rego, order Rego, and payment Rego. And then we have the Docker compose file, which will run the different services. So Keycloak, as I told you, will be running as a container. OPA again with the Rego files. Postgre is the DB which we'll be using. Jaeger will be for our telemetry. Gateway will be based on our the image which we will be having in our Docker file, which is this one we are using. So gateway based application. The same way in the we have the order API, inventory API, and your payment API. And then each of these services will have their own Docker setup running. I have gone ahead and run the application, made it up in and running in the Docker setup. Let me just quickly show you the current status of the containers. So all the containers are up and running. I'm seeing one error in Keycloak. Let me quickly check that. Let me try logging into Keycloak. So this seems to be working fine. And let's first go to the users. And in the users, we will see that we have Alice. Alice has a basic setup. She has the attribute for the tenant ACME, and all the setup is ready for her role mapping, why she should be able to do orders read and orders create. And in terms of other users, you can see Bob and Eve. The Bob and Eve also have the tenants, their own respective tenant, which is Globex, and their role mappings are also present. And then similarly, you can see different clients. So we have order API, inventory API, client order API, and payment API. These have their own scopes. They have their own service account enabled and their own credentials, which we have to use to call the token and get the access to the APIs to identify ourselves. Now moving on, we can also show the OPA, which is running on 8181. So let me run the OPA. As you see, it should return false by default. If you remember, we were talking about returning the OPA, the by default OPA should be returning as false. So anything which we try to do first will be default will be false. Next we will go to the Jaeger. Let's run the Jaeger and see if it is up and running, and it is registering. It is looking for any operations which are happening. It doesn't have anything yet because we haven't triggered anything. And also we can check if OPA is healthy through the URL call. So let me see, and it seems to be returning empty, but we can see from the containers that it seems to be running fine, and OPA seems to be running perfectly fine. So now let's go ahead and log into the Keycloak, and as we saw the Keycloak, we are able to see all the users. So let me go back to the Keycloak now, and you can see we have all the setup in place along with the tenants. And then let's go ahead and do some call to get the token. So I will open up a terminal, and I will run a request. So for Alice, I am going to run a call to connect to the Keycloak realm, passing the token, the request, and we should be able to get a token back. And let's see the token now. And it should be, and when we go ahead and do the JWT IO on this, so let's open jwt.io and decipher this token. So if you see at the right hand side, Alice has audience of order API and gateway API. Roles, we just saw orders.create and orders.read, and some other related details of Alice is coming up here. Now let's go back and try to do a post of the API call with this token. Now let's go ahead and create a token for Alice. So let's go ahead and do that, and get the token. Let's inspect the token now. So I'll just copy this and go to the token, and as you see, she has order.create and order.read. I'll go ahead and put that in the postman. The postman collection is this one. I will just go ahead and paste it, and I will be creating the body tenant ID same, but I will just do it as to quantity again 21051 and INR. Let me send this, and as you see, the creation has successfully happened, and it is authorized status for the tenant ACME. So this was pretty much about the implementation with Zero Trust architecture. Hope you like the video. If you like the video, press like and subscribe to the channel. Have a nice day.